so starting Monday, we will be talking about material that won't be on test 3. Okay, so today is the wrap up of test 3 material. So if you haven't started studying already, you should as soon as possible. The test is, as usual, there's a review posted online. I hope that when you go through and you read the bullets, you challenge yourself to think about what kinds of problems could correspond to those ideas and the different, like, how are all of these things related? What are the big pictures? What are things that we've done in class related to those? What are things I've asked you to do for homework and things like that, okay? As always, you should study the quizzes. Quiz solutions are also posted. Yep, I think that's all I got for that, okay? So, and the answer to the question about formulas is I will give you formulas for cones and spheres, but you should know everything else.
Okay. Awesome.
Mm-hmm. Okay. Are there any other questions before we do some fun problems? Fun? No? Okay. So like I said, today I thought that we could just make sure that we're really good with these figuring out how to tackle what I'm deeming applied optimization problems, okay? So the point here is that the mathematics that you use to solve these problems is nothing new, right? It's everything that we've talked about with regards to how you can infer information about an accumulation function based off of information from the rate of change function and the rate of change of the rate of change function, okay? So all of the stuff that we've talked about, for instance, if the rate of change function is positive, what do you know about the accumulation? Dakota? It's increasing. So the it is the accumulation function is increasing, right? And then if the rate of change switches from positive to negative, what could you say about the point at which it switches? George? Okay, we'll deal with that in a minute. Okay, but my question was, if the rate of change changes sign from positive to negative, then what can you say about the accumulation function? That you have a critical point? Okay, could you say more than that? So the rate of change changes sign from positive to negative. What can you say about the point at which that happens? Yes. An inflection point? Yeah? Okay. So, all right. So, yes, local maximum. So here's what I said. I said the rate of change changes from positive to negative. Okay? So if the rate of change is positive, that means that the accumulation function is increasing, right? And then if the rate of change is negative, that means the accumulation function is decreasing. So the point at which it changes from increasing to decreasing would be a local max, okay? So I think the inflection point, you're thinking of when f prime, when the rate of change changes from what to what? It can't be positive to negative from increasing to decreasing. So this is, again, what I was trying to warn you guys about, right? So a lot of people like to interchange positive and increasing and negative and decreasing. And you can't do that because they have different meanings, right? Just completely different meanings. And the implications of their meanings are significant, right? So if the rate of change changes from increasing to decreasing, okay? So if the rate of change is increasing, okay, that means that we either, depending on whether or not the rate of change is positive or negative, right? We could either be looking at something like this or like this, right? To start with. And then if the rate of change is decreasing, okay, again, depending on whether or not the rate of change is positive or negative. So if it's positive, you'd have something that looks like this. And if it's negative, you'd have something that looks like this, right? Okay. But so then when you piece these together, so like piece this one with this one, for instance, together, then you've got an inflection point. Okay. And likewise, put this one together with this one, and you've got something like this. And again, you've got an inflection point. Okay. So it really matters that you pay close attention to the difference between increasing and decreasing, and then positive and negative. The implications are very different. Okay. All right. But in particular, this thing is sort of the key to doing optimization, right? So when the derivative changes from positive to negative or from negative to positive, you get extrema, right? You get either local maxes or local mins, okay? And the whole point is that, okay. So at this point, though, what is the value of the first derivative? The rate of change at these points is 0, okay? So if you're looking for places where maximums or minimums might be, then the route to find those places would be to do what? Find places where the derivative is 0, right? So, but of course, all of that relies on you already having a function to start with, right? So that tends to be what's tricky about optimization, okay? So this example is from the packet that I gave you on Monday, and then we'll get to the new packet after this, okay? So in this problem, we have a square-based box-shaped shipping crate that's designed to have a volume of 16 cubic feet, okay? The material used to make the base costs twice as much per square foot as the material in the sides, and the material used to make the top costs half as much per square foot as the material in the sides. What are the dimensions of the crate that minimize the cost of the materials? Okay. So this is a really reasonable question to ask if you're running a shipping business, right? You want to figure out how to minimize your costs. So like, I don't know, anybody run an eBay business? I heard there's good money in it. No? Nobody does that? Is that like not a thing anymore? eBay? It's still a thing, right? Still a thing. Okay. Anyways, okay. So if we're trying to tackle this problem, okay, then you have to so in a similar manner that we did related rates, where we sort of had to like visualize what's going on and try to create some sort of setup and be very clear about what we're aiming for, you have to do the same sort of thing with these types of problems, okay? So I'm going to sort of like walk us through this one, and then I'm going to give us time to like actually work, because I feel like it's better for you guys to actively do math instead of just listen to me do math, okay? So, okay, but I want to give you at least sort of like a strategy of attack. So where would I start? Well, I would definitely start with a picture because they help me, okay? So I've got a square-based box-shaped shipping crate, so something like this, right? And so the thing that we know about this box is that the base is a square. So that means that I could label the sides of the base with the same label, right? Because it's a square. And then there's some height to this box, okay? What do they tell me about the box? So if I want to label what they tell me that the volume of the box is 16 cubic feet. Okay? Now, they immediately switch to start talking about the cost of the materials to make this box, right? So they say that the base material costs twice as much per square foot as the material on the sides. And then the material used to make the top costs half as much as the material on the sides. Notice they never tell me how much the material on the side costs, right? Like, I don't know how much that costs. So I'm just going to say that it costs some amount. So material on sides costs K dollars per square foot. So if I call that cost K, what could I say about the material on the base, for the base? It costs 2K, right? Twice as much. And for the top is half as much, so K over 2. Is this okay? So far, so good? Okay. So I'm literally just going through the sentences and recording the information that they're giving me. So then I get to the last question, I get to the actual question, and they say, what are the dimensions of the crate that minimize the cost of the materials? So we want dimensions. So my final answer is going to look like the value of the length, the value of the width, the value of the height, okay, that do something, that minimize the cost, okay? So I'm underlining these things because that's what's going to help me figure out what to do, okay? So I'm trying to minimize cost. Well, if I'm going to minimize cost, then I better have an equation for cost, right? So how could we write down a formula for cost using the information I've written down so far? Yes?
A plus K plus K over 2.
Well, so notice that these are costs in dollars per square foot. So imagine you walked into Home Depot and you were buying...
So 8 times?
So, yeah, so you're buying like, you know, PVC pipe by the foot, right? And it costs $2, and that's excessive, but like 50 cents per foot, right? So then however many feet you buy times the cost per foot is how you calculate the cost of the PVC pipe, right? I used to use fabric as an example of this and then realized that nobody goes into fabric stores anymore. Would that example work for you guys if I use that? Some of you, yeah? Okay. So that's another way that you could think about it, right? You buy fabric by the yard and it costs so much per yard. Anyways, so, okay. So in order to talk about the cost, right, you can't just add up these K values because those are by like amount of money per unit of area, okay? So in order to talk about the cost, let me just write it this way. So the cost is going to be the cost of the side, but I have to multiply. So this is the cost of the material of the side per square foot. So I need to then multiply that by how many square feet there are to make up the sides, right? So how many square feet are there to make up the sides of this box? So each side has an area of what? X times H, right? And there's 4 of those sides. So 4XH, okay? What about the cost of the base? So the area of the base is X squared. The cost per square foot is 2K. Okay. And then for the top, right, the cost per square foot is K over 2, and the area of the top is also x squared, right? So here I have an equation that gives me the total cost, but what were you going to say? Oh, okay. So here I have an equation giving me the cost, the total cost of making my box, right? But remember, my goal was to minimize the cost. So what needs to happen before I can try to find a minimum? We do need to do calculus. I agree. In particular, what kind of calculus is about to happen? What are we going to do? We're going to find the derivative, because we know that when the derivative is what? 0, then what happens? We might find a local max or min, right? So, okay. So if I wanted to take the derivative of this, is that looking good? So right now, this cost function is a function of x and h. That's no good, right? Because I don't know, for instance, how, like, just don't know, right? What's up with these things? So, so what I want to do is rewrite this cost function as a function of one variable, right? Because that's what we know how to work with right now. So, most of these terms have x's, so I'm gonna vote for getting rid of the h. But how do I do that? We had volume up here, right? So they told us some information about the volume. So in particular, the volume is 16, right? So volume is 16. But I could also express the volume, rather than just using V for volume. Since I have dimensions of this box, I can actually write down the equation for how to find the volume, right? So how do you find the volume of this box? X times h, right? So x squared times h is 16. So that means h equals 16 over x squared. And so now we can actually write our cost function as a function of one variable by substituting what we just found for h in terms of x. I'm going to go ahead and add these up. So this is 5/2 k x squared, combining like terms. Okay. Cool. So are we ready to optimize? What do you think? Yeah? I would clean it up just a little bit, but that's because I'm OCD and I don't like having to use the product rule when it's completely unnecessary. So I would, instead of leaving this expression, this term as it's written, I would clean it up a little bit, and I would say that's, what, 64k over x, and then plus 5k over 2 x squared. So now when we find the rate of change of this cost function, right, the 64k is just a constant. The rate of change of 1 over x is negative 1 over x squared. Again, this is a constant, but then times 2x. So I can get rid of the 2. Yeah. Okay.
What's the easy way to use this to get from 64k over x to the derivative of negative 64k over x squared? There we go.
Cool. So what were we in the middle of? Why did I just take the derivative again? Why did I want to set it equal to 0? Because that's where we might find a local max or min. Okay? So while we're doing all of this stuff, I don't want you to ever lose sight of why we're doing it, right? We get local maxes and mins when the rate of change is 0 because the graph pauses there, right? And so like near that point, there's not going to be any local increasing or decreasing happening. It just pauses and it hangs out, okay? So if we set that equal to 0, what happens? We get negative 64k over x squared plus 5kx equals 0. This is where I find a lot of calculus students struggle because this is algebra, and it's been a while since you've been asked to do algebra, okay? So, so if you feel like you're a little shaky on your algebra and you want to like meet me in office hours to brush up on some things, we can totally do that, okay? Because I don't want your, you know, I don't want the length of time since you've practiced your algebra skills to impact your calculus grade. That would be unfortunate, okay? But with that being said, how could we go about solving this? You can factor out a k, but so one of the problems is the thing that I'm trying to solve for is x, and it's in the denominator. That's bad, right? You don't want the thing you're solving for to be in the denominator. So the first thing I would actually do is multiply everything by x squared to get that out of the denominator. And so then you get negative 64k plus 5kx cubed equals 0. So then add the 64k, divide by 5k, take the cube root of both sides. And you get that. Yes? Yep. So this term times x squared cancels the x squared. This term times x squared makes it, that's a cubed. Yep. Okay. So remind me once again, what is the meaning of this x value? This is where the graph pauses, right? This is where our accumulation of cost takes a breather, okay? So how do I determine whether or not that value gives me a maximum or a minimum, though? Because this could be where the cost is maximized, right? And that would be bad for business. So how do I check it out? For sure. So we have a couple of options. We can use the first derivative since we've already found it, okay? So the way we would go about using the first derivative would be to say, okay, well, we know that the first derivative is 0 at this x value, okay? So if I check just a little bit to the left and a little bit to the right, what values would I want to have in order to be able to conclude that this x value is where a local minimum occurs? To the left of this x value, I'm hoping that the derivative is negative. And to the right, I want it to be because that would mean that our accumulation function is decreasing and then increasing. So we'd have a local min, okay? So for sure we could do that. So it's, but that would require me to have any idea of what that x value is, which I don't. So since I don't have a calculator handy, then I'll do the other option, which is to take the second derivative, okay? What's that? So that'll be, it's not 64. So how would I rewrite this first term to make this derivative easier to find? So negative 64k times x to the negative 2. So this whole part right here is a constant. So the derivative of x to the negative 2 is negative 2 times x to the negative 3, right? So if I multiply negative 64 times negative 2, I get positive 128k over x cubed. And then the derivative of 5k times x is 5k. Okay? So if I were to plug in this x value into the second derivative, will I get a positive or a negative number? So this is a positive number. If I cube it, I get a positive number. And certainly k better be positive because it's the cost of material, right? Like nobody's paying you to take their material, okay? So, so that means I'm adding two positive things. So this will be positive at this x value, which means that the accumulation function, the cost function, is concave up, right? So that looks like this again. Ah, sweet. Okay. So this is how you verify that your critical value gives you a minimum or a maximum. Okay. Have I answered the question? No. What was the question? What did I want? Dimensions, right? So, yeah. So the answer is going to be this number of feet, right? By this number of feet, by what? By h. So h, we did some work to find in terms of x over here. So that would be 16 over all of this stuff squared feet. Okay? So those are the dimensions. Okay? And so now we've answered the question. Adam? Excellent question. Okay, so every once in a while you'll come across a problem where you only find, for instance, one critical value, and then you check it out and you realize it's not a maximum when you wanted a maximum, and you realize it's a minimum, for instance. Okay, so if the problem is asking you to find where a max or a min occurs, then there's going to have to be some other restriction in the problem that will impose the possibility of a max or a min. So what do I mean by that? I mean, so is it okay for me to erase the screen? Okay. So I mean, for instance, and I'm going to go back to just thinking about graphs for a second. So let's say that I have the graph of a function. That does something like this, okay? And I want to find a maximum between this x value and this x value, okay? So if I, took the equation for this graph, whatever that is, I find my critical values in the normal way, and I find between 2 and 7, I find a critical value at 3, right? But that critical value gives me a minimum, a local minimum, and I wanted a maximum. So on this interval, where are the only other, where else could I look? Well, if we focus on this graph, right? So on this interval, I'm going to color it in green, right? Here is what the graph looks like. Whoops. Here's what the graph looks like on that interval, right? So where is the maximum on this interval? What does that mean? Okay. Yeah. So this is the maximum, right? We can see it. It's right here, right? Whatever that y value is the maximum, and it occurs at an endpoint of that closed interval. Okay? So there are technically two scenarios in which you can get extremum, right? So you can get extremum from critical values where the graph pauses, right? And you actually have like these nice bumps, if you will, okay? But if you have a closed interval, then you can also have extremum at the end values of those intervals, okay? So that's the second place where it comes up. So you legitimately have to check, right? Don't assume just because you found a critical value that it gives you the answer, right? There are other scenarios in which you can get maxes and mins at places where the x values are not critical values, okay? Okay, I've done entirely too much talking, as usual. So let's look at the problem that I gave you. I'm thinking, so if you didn't get one, come grab a handout. So I'm thinking, because I talked too much, that the best problem really is the first problem. So what I want you to do is try to tackle this first problem. Take maybe 5 to 10 minutes to try to do it. Okay? Try to solve it. So I just saw the time, so we better do this quickly. Okay? So, so I snuck in a picture to hopefully help you if you were stuck on that part. So remember, when you draw pictures, you only want to label things as constants that are actually constant. So in this case, the only thing that remains constant is the distance from the island to the shore and the distance from the point closest to the island, and the town is 13, right? But where you actually row to on the shoreline, that could be anything, right? We don't know what that is, so we're going to use a variable x to label that, and then I can label the rest of the distance 13 minus x, because that's what it would be. And then, so that's nice, right? But then they gave me other information, right? We were given that you can row at 3 miles per hour, and you can walk at 4 miles per hour. And what did we want? To minimize time, okay? So I need a time function. So I've got a picture about distances. I was given information about rates. How do I get to time? What's the connection between distance, rate, and time? Distance equals rate times time, right? If you want to know how far you've traveled, if you're traveling at 60 miles per hour for 3 hours, you multiply the rate times the time, right? That'll give you the distance. So if I want time, though, then I should probably rearrange this to be time is distance over rate, okay? But notice on this journey, I'm traveling in different ways. I'm going to travel by rowing, and I'm going to travel by walking. So if I'm talking about my total time, that's going to be time rowing added to the time walking, right? So in order to describe the time rowing, I need the distance that I row. Well, the distance that I row is this dotted line, right? Can I find out what that is? I can, because I have a right triangle. So this length, using the Pythagorean theorem, is the square root of x squared plus 16, okay? So what I'm actively doing right now is creating a time function in terms of x. So the rowing time is the rowing distance divided by the rowing speed, right? The rowing rate. And the walking time is the walking distance divided by the walking rate. So now I have a time function, and I wanted to minimize it. So now I can start doing calculus, right? So you take the rate of change. So I'm doing this fast because we're running low on time, right? And you get this, okay? So this is the rate of change of my total time function. I'm looking for a minimum, so I'm gonna wanna set that equal to 0, okay? If I solve this thing for 0, do you want me to go through the steps, or can I just tell you what it is? Steps, okay. So, so I've got 2x over 3 square root of x squared plus 16 minus 1/4 equals 0. So I'm going to add 1/4 to both sides. I can get rid of denominators by multiplying both sides by the denominators of both sides. So I end up with 8x equals 3 square root of x squared plus 16. Have I made any mistakes so far? I am prone to error when I'm doing things quickly. Are we doing so good so far? So far, so good? Okay, so I've got the thing that I want under a radical. That's bad. So I'm going to square both sides to get rid of the square root. So I get 64x squared equals 9 times x squared plus 16. I feel like I'm getting different numbers than what I did when I did this before. So far, so good? Okay, great. So then I can distribute the 9. Rashay, you look distraught. Yeah. Yes. I multiplied the 4 by the 2x. So I'm going to distribute this 9 and subtract the 9x squared. So 64 minus 9 is 55x squared equals 9 times 16, which is 144. So then I can divide by 55 and take the square root. Okay. Now, so you get two answers. You get a positive x value and a negative x value. What would the negative x value mean in this problem? You row away from the town. That's not going to minimize time, right? That would be bad. So we're going to take the positive x value as the most likely candidate for where our minimum will occur and test that x value. So this is the critical value that we suspect will give us the right answer, right, for minimizing time. And so we can test that in one of two ways, right? We can plug it into our first derivative, or sorry, we can plug in a number slightly less than that and a number slightly larger than that into our first derivative and see if it goes from negative to positive, the it being the rate of change function, because that will give us a minimum. The second possibility would be to take the derivative again and plug it into the second, and plug this x value into the second derivative to see if the accumulation function is concave up or concave down at that value. Okay. I'm going to post solutions to this worksheet online with the YouTube video. I think I go through some of the details, yeah. Okay. Have a wonderful, safe weekend. Question? Oh, sorry. You wanted to talk about that.